Hello and welcome back to the video lecture series for ECE-340. I'm your instructor, Dr. Bradley Duncan. Today we're going to be looking at the correlation coefficient. The correlation coefficient is a really interesting parameter. Really it's going to use the covariance in a normalized fashion, and it's going to give us some information that you may unknowingly already be familiar with. So for example, imagine you're watching the evening news and the reporter tells you that some pharmaceutical company has developed a new drug that has been shown to be correlated to about the 80% level with patient improvement, meaning that this drug company has developed a new drug, patients with some illness take the drug, and about 80% of the time they start getting better. What he's really referring to is the correlation between administering the drug and a patient improvement. That's a measure of correlation coefficient. We're going to see how to calculate that today. So, before we do, I need to give you a bit of a review. Review from the last lecture. First of all, remember the concept of covariance. Oops. This is the expected value of the product of xy minus the mean of x times the mean of y. We saw that last time. This is covariance. All right. Variance for x is the normalized power in x minus the square of the mean. And similarly, the variance for y equals a normalized power in y minus, drawing my muse backwards again, all right, so these two are variances. Those two are variances. Another thing I want to remind you is that we had another thing called the correlation. And correlation is not correlation coefficient. That's a different concept. We're going to get there in just a minute. Correlation was the expected value of the product of x and y, meaning that my covariance can be written as the correlation minus the product of means. Okay? All right. All right. So that's enough review for what we need right now. Correlation coefficient. All right. Correlation coefficient is going to use the covariance uses covariance in a normalized fashion. And we'll see that in just a second. It's going to be a quantitative measure of the degree, dE, the degree to which two random variables influence one another. All right? Influence. correlation coefficient does not tell us the mechanism of influence. Does not. Does not address the mechanism of influence. And is not related to the rate of influence. And we'll have to explore the second statement through some examples a little bit later on. All right? Just hang on to that for now. All right. The correlation coefficient is designated this way. Rho sub xy. Correlation coefficient is my covariance divided by my standard, a product of my standard deviations. All right? Covariance divided by the product of my standard deviations. Expand it out in all its glory. It's going to be my correlation minus the product of means divided by the square root of the variances. You'll notice that both of these things inside the radical here, this one is the variance of x, and that one is the variance for y. Square root of variance is standard deviation. Okay? So let's peel apart the concept of correlation coefficient by doing a series of examples. Well, very clearly, if x equals y, my correlation coefficient equals 1. If x equals y, our correlation coefficient equals 1. My correlation in the numerator will just be the expected value of x squared minus mu x squared. Sigma x. You'll notice that my numerator is now the variance of x divided by of x, 1. Okay? All right. What happens if x, now let's say it this way, if y equals negative x? All right. Well, my correlation, which is the expected value of x times y, will just be the expected value of negative x squared, which is negative expected value of x squared. All right. The mean of y is the expected value of y, which is the expected value of negative x, which is negative expected value of x, which is negative the mean of x. All right. My correlation coefficient then in the numerator is going to be negative that, and this is the negative of the variance of x over the variance of x, and that is minus 1. Okay? So if x and y are off by a sign, if x equals negative y or y equals negative x, then what this is saying is that if x increases, y always decreases. That's what a correlation coefficient of minus 1 means. Up here, if x increases, then y always increases. That's what correlation coefficient means when it's 1 or minus 1. So if x equals y, if x increases, then y always must increase. If x equals minus y, then if x increases, y must always decrease. All right? It can't be more influential than that. All right, let's look at another one. What happens if x and y are statistically independent? What happens if x and y are statistically independent? Well, rho x y equals that's my correlation coefficient in general. If my random variables are statistically independent, we saw earlier in the previous video that my correlation is just ux, uy, oops, that's not squared. All right, and that is clearly 0. If x and y are statistically independent, then my correlation coefficient is exactly 0. If x doesn't relate to y in any way, shape, or form, they are completely, totally uncorrelated. When the correlation coefficient is 0, that means x and y are uncorrelated. Okay? Now let me say this. If x and y are independent, then they are uncorrelated. However, not all uncorrelated random variables are statistically independent. That's important to remember. Not all uncorrelated random variables are statistically independent. I can come up with rho sub xy equals 0 in a variety of cases, and I think you'll actually see some of that in one or two homework problems. All right? All right. So, from our previous work, notice that my correlation coefficient will always fall within the range plus to minus 1. All right? If rho x y equals 0, we have what we call uncorrelated random variables. If the absolute value of rho sub xy equals 1, we have fully correlated random variables. Fully correlated random variables. All right? It can be fully positively correlated, or it can be fully negatively correlated. If x always increases and y also always increases, then my correlation coefficient is 1. If x increases and y always decreases, I get a correlation coefficient of minus 1. The sign only tells me the direction of change of one random variable due to the influence of the other. All right? It's still 100% correlated if my correlation coefficient is minus 1. All right. But keep in mind, correlation coefficient doesn't tell me the mechanism of influence. And it doesn't address the rate of influence. We'll explore that next through an example. It only addresses the tendency to influence. Only addresses the tendency to influence. All right, let's explore that rate of influence issue a bit. All right, let's let y be related to x through a linear transformation. Okay. Linear transformation. And let's find the correlation coefficient. I need a few pieces here. One, I'm going to need the mean of y. And this is going to be a times the mean of x plus b. We've seen that before. We're also going to need the variance. The variance for y. Right? Plug in y and mu sub y. My b's are going to cancel. All right, and I get the expected value of, oops, I need to raise this to the second power right there. I get a squared times x minus ux, quantity squared. And this is a squared times expected value of x minus ux, quantity squared. This is just clearly a squared times the variance of x. All right. And the third piece is the standard deviation. That's just going to be plus or minus a times the standard deviation of x. All right. And I'm going to have a plus sign if a is, let's make that more clearly an a, if a is greater than 0, and a minus sign if a is less than 0. And I need that because standard deviation is always stated as a positive quantity. Standard deviation is always stated as a positive quantity. We've never discussed a negative standard deviation. So if a happens to be negative, if a right here happens to be negative, I have to change the sign. Well, it's a dual root issue, right? When I take the square root of the variance to get standard deviation, I get plus or minus the result. Okay. Let's keep moving. The next piece I need the covariance. Covariance can be written this way. That's a minus sign. That's covariance. Plug in what we know. We're going to have plug in y. I get an a x plus b, and then mu y is a mu y plus b. And this will be expected value of a times x minus mu x, quantity squared, or just a times variance of x. Okay? Hopefully you can check me on the math there. All right. So then we have all the pieces of the puzzle to calculate my correlation coefficient. So my correlation coefficient equals my covariance divided by the product of standard deviations. This is a times the variance of x divided by the variance of x times plus or minus a times the variance, standard deviation of x. Sorry, I have standard deviations of x in the denominator. And this turns out to be plus or minus 1. Clearly, it's plus 1 if a is greater than 0 and minus 1 if a is less than 0. All right, so the factor a describes the rate of influence. That's the slope. Okay? So, for example, if A is plus 10, for example, if A is plus 10, if X increases by 1 unit, Y will increase by 10 units. Okay? That's a rate of influence. Correlation coefficient only tells me the tendency of one random variable to influence the other. All right? From a correlation coefficient perspective, up here, if, we'll assume that A is positive, if A is greater than 0, if A is greater than 0, when X increases, what that says is if A is greater than 0, when X increases, then Y always, 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 always increases. Correlation coefficient addresses the tendency of one random variable to influence another. It doesn't discuss the mechanism of influence, and it does not discuss the rate of influence. Okay? Conversely, if A was less than 0, if X increases, then Y would always, always, always decrease. Okay. Correlation coefficient tells us a lot, but it doesn't tell us everything. Let's do another example. This is an interesting example because of what it looks like at first, but is actually not. All right. Now I claim to you that this probability density function is a proper probability density function. It's got a volume of 1 and all those kinds of things. At first glance, if all you looked at was this 8 times xy, you might think that that is separable and a product of just x and y, but in fact, due to the nature of the range for x and y, my random variables are not statistically independent. Okay? The range over which random variable y exists, range over which random variable x exists is dependent upon the current value for y. All right? And what we're going to find is we want to find the correlation, the covariance, and correlation coefficient. This is one of those examples where it's the method, the steps that I employ are going to be hopefully helpful to you, but the final result is not particularly interesting. It's the math that's of interest right now. So let's find the correlation. This equals x, y times my joint PDF. All right. And this, my range stipulations tell me that my integral for y goes from 0 to 1. My integral for x goes from 0 to y. X y times 8x y dx dy. About to run out of room. This is going to be 8 times the integral from 0 to 1 of y squared, integral from 0 to y x squared dx dy. So I'm going to do that integral first. And I ran out of room, so let me go to the next page and I'll rewrite this. Let me just remind you where we are. My correlation, we're at this point. 8 times the integral from 0 to 1 y squared, integral from 0 to y of x squared dx dy. Right. So since x depends upon where we are with y, we're always going to do our x integrals first in this particular example. Continuing on, we get this 8 integral from 0 to 1 y squared. Perform the integral in x, I get a y cubed over 3 dy, and that is 8/3 integral from 0 to 1 of y to the 5th dy, and that's going to be 8/3 times 1/6 or 4/9. Okay? All right. How about we need to find the covariance. We need to find the mean of x and the mean of y first. So let's draw a line here. The mean of x going to be integral from 0 to 1 in y, integral from 0 to y in x, x times 8xy dx dy. That's going to be integral from 0 to 1, 8y to the 4th over 3 dy, and that is 8/15. All right. In all cases, I'm going to integrate against x first. I'm going to integrate against x first, and I'm skipping some steps here, folks. I want you to go check my math and make sure that I'm getting the right results. I'm integrating against x first because the range of x depends on the current value of y. All right, I still need to know the mean value of y. Mean value of y is going to be integral from 0 to 1 in y, 0 to y in x of y times 8xy dx dy, and this is integral from 0 to 1, 8y to the 4th over 2 dy, and that works out to be 8/10 or 4/5. Okay? Again, I skipped some steps. I'm going to let you check me on that. I'm integrating against x first in all cases. So, the second part of this problem, I asked to find covariance, and this is just the correlation minus the product of means, and that turns out to be 4/9 minus 8/15 times 4/5, and that turns out to be 4/225. That's my common denominator, for goodness sakes, and that is 0.0178. Okay? Okay. Now I need to find the mean squares. The mean squares are going to be required for me to actually finish calculating the correlation coefficient. So the mean squared value of x, the normalized power in x, all these integrals are going to follow the same. I'm going to integrate from 0 to 1 in y, from 0 to y in x. X squared times 8xy dx dy. And that's going to be the integral from 0 to 1. Where am I? 8y to the 5th over 4 dy. That turns out to be 8/24 or 1/3. Similarly, the mean squared value for y, with a normalized power in y, is the integral from 0 to 1, integral from 0 to y in x, y squared times 8xy dx dy, integral from 0 to 1, 8y to the 5th over 2 dy, and that is 8/12 or 2/3. Okay. Then I can calculate my variances. Variance is the mean squared value minus the square of the mean, and that is 1/3 minus 8/15 squared, and that turns out to be 11/225 or 0.0489. The variance in y is the mean squared value in y minus the square of the means, and that's going to be 2/3 minus 4/5 squared, and that turns out to be 6/225 or 2/75, and that's 0.0267. All right, that's all the pieces we need to finish off this problem. So my correlation coefficient after all this is my covariance divided by the product of standard deviations, and that's going to be 4/225 divided by the square root of 11/225 times 2/75 And that works out to be 4 divided by square root of 66. And that turns out to be 0.4924. Whew. Goodness gracious. Okay, I would call that modest correlation. All right, modest correlation. Okay, not perfect correlation. What that tells me is that if X increases, about 50% of the time, Y is going to increase. All right, and it's going to increase positively. One increases, the other one's going to increase. If X increases, Y is not going to get negative. You'll notice that there's an implicit plus sign here. All right, X increases, Y increases, about half the time. All right. Once again, the actual numerical result for this particular example is not all that interesting, except to show you a result where we have modest correlation. Everything else I did today was either 0 or plus or minus 1. And hopefully some of the techniques in doing the math here will help you out. Anyhow, that's all I have for today. As usual, if you have any questions, please feel free to contact me at your earliest convenience, and I'll answer all questions as thoroughly as I am able. Have a nice day. Bye-bye.